And hello, welcome back to Turbulence Modeling video series. We're going to continue in the last. We're going to continue what we did before. So let's see what this actually amounts to. What this actually results in. If we just rearrange the equations around, we know that the y plus here is always the same because they have this iteration code. They have this iteration code over here. That while this is some tolerance thing, then you just while this is less than some tolerance and your iteration number is less than the max iteration, y pli and more than v small, blah blah blah, you keep iterating. So that's what you're doing. So yeah. So that's what you do. So we were stopping here last time with line 161, and then we want to see whether this equation can in some form be related to this equation over here. And then we'll have this highlight delta u plus equals to some function like this. So I'll put this in green. Okay. And the next thing I want to look at is this. Let's start manipulating this equation. No color. Alright, so again we swap around both sides. So this I'm going to swap here, and this I'm going to swap here. Alright, so let's do term by term. K Reynolds over y plus. So kappa Reynolds over y plus. If we are familiar with that, then we'll kind of notice straight away that this is actually, from our last calculations, of course, kappa Reynolds over y plus. Yeah. Where is it? Yeah. Kappa Reynolds over y plus is just equals to kappa times u plus. Okay, so that's easy for us. We'll just copy this down. Kappa into u plus is equals to kappa Reynolds over y plus. So this is just kappa into u plus. This one will become 1. Okay, so I'll just get this out and I'll paste it here. Hopefully I got that right. Okay, so I have a kappa u plus here, and then 1 times 1 minus y plus g prime. Okay, so yeah, let's start getting rid of some unnecessary terms. Okay, first we can get rid of this 1 plus 1 term. This one we can mop it up. Delete. Okay, so delete here. Then I'll just get minus y plus g prime. Okay, so yeah, that deals with this y plus term. Y plus term is here. Yeah. Yeah. Okay, so that maybe I should just do this. Yeah. Less confusion. Or in fact, I can just take this whole thing out, paste it here, and I'll just copy and paste this here. From there on, you can quickly see that these two will cancel out. Okay, and then finally we have a u plus equals to, okay, u plus equals to 1 over kappa. Okay, then we'll just copy and paste this whole thing here. And immediately we can see, okay, we have this one, the ln EY plus, which is the smooth part, and then this is the modification that the rough part actually does. So we can just expand that out into this minus 1 over kappa times g. There we go. Alright, 1 over kappa times G. So we kind of take a look at, we compare to this. Okay. Compared to this, you can see the immediate resemblance. 1 over kappa ln EY plus is this part. And then this minus 1 over kappa, this 1 over kappa G equals to this U plus over here. So, in effect, we will have this looking, this kind of thing. 1 over kappa G equals to 1 over kappa ln this whole expression here. So in effect, G equals to what we are familiar with, this logarithm of whatever this is. Okay, so what is G in OpenFoam? Well, what is G in this OpenFoam new T wall function? Alright. Then let's take a look at the code again, or let's take a look at where things were defined just now. G equals to ln 1 plus k roughness ks plus. Okay, so this is this. G equals to 1 plus ln of a k roughness ks plus. Okay. Alright, so this is in the OpenFoam. Obviously, we do see this one thing over here, and then we see this hs plus equals to this ks plus. So what we have in this denominator is exponential 3.25 over k. Okay. So if k roughness equals to 1 over exponential 3.25 times 0.41, then we will get the following. And k roughness can be worked out to the following, equals to 1 divided by exponential 3.25 times 0.41 close, and it equals to 2.63. So it's not exactly 0.5, but we can adjust as so if we wish. So just note that yeah, this is what we get. All right. If we were to use this formula over here, then yes, ks plus is supposed to be somewhat of 0.26. So let me just bring you back to here. Okay, I wanted this link. Okay, I'll scroll back down, and yeah, okay. So this is the wall function approach paper that we have been liking to use. So this is the shift u delta u plus can be provided in a more complex, slightly better form like this. Okay. Okay, this is from Colebrook's data. Of course, there's another form by artificially increasing some turbulent viscosity at the wall. This I didn't quite go into. I'm more interested in this because it's easier, very easy to compare. Okay, so yeah, so this is what we get here. K roughness is about 2.638. So this is something important to note. So I'll just highlight it here in maybe purple, pink. Okay, pink will do. Yeah, pink's a very bad color. It's very painful for my eyes. I mean, it's a nice color, but not for now. Cyan is better. Okay, so cyan, we use a cyan color to identify, okay, this K roughness, if it's equals to this, if we use this expression here, K roughness should be this much. Okay. Of course, yeah, this KS plus, you can of course do some scaling factor. Okay, if your scaling factor wasn't 1, because remember there was a scaling factor just now. Yeah, okay. Yes, KS plus. We have a scaling factor. We have this F roughness here. Okay. So we can use this scaling factor to kind of bring. Okay. We can also use this, the scaling factor thing, but that kind of throws us off a little bit if F roughness is not equals to 1. But of course that allows us to use K roughness equals to 0.5, and then use this F roughness to kind of compensate, just to make it this number, so that K roughness times KS plus equals to yeah. So we can adjust K roughness KS plus equals to 0.5 KS plus, as long as 0.5 times F roughness HS plus, okay, that must be equals to this number, to HS plus, equals to 0.226 something, 2638 times HS plus. And of course makes your F roughness a little bit different, and it will make it, yeah, where will it affect? It will only affect in this KS plus model. Otherwise, if it's the smooth model, it won't really matter. Okay, but this is, you'll only affect the roughness part. The smooth part it won't affect. It will only affect the roughness part. So what I was trying to say for the last 2 to 3 minutes is basically this: if we want this number K roughness to be equals to 0.5 as we set in our default settings, we will have to alter the F roughness here to kind of compensate, so that F roughness times 0.5 equals to this 0.2638. Where F roughness will then become this number divided by 0.5, and then it will be roughly 0.5253, something like that. So that's another way of approaching this problem, so that we can make it consistent with the formulas we've been using. But this is for the regime of KS plus more than 90. We can look at the second regime to see what is being used here. Okay, so we roughly understand the first regime. Let's see the second regime. Okay, so this is the second regime. Okay, so this is over here. All right, so this one looks a little bit more scary, but yeah, I mean, it's just a different way of defining this y plus g prime, right? Because eventually this y plus g prime term won't really matter, because we just cancel everything out anyhow. All right, but okay, we'll just leave it as that. Yeah, we'll leave it as that, and we'll just see this what this actually does. All right, so we take a look at this regime. And yeah, what about this regime do we need to take note of? Well, we know that from this formula, we see that this y plus g prime doesn't really matter, because it gets cancelled out anyhow. So we see in here, this formula is the same whether we have the second regime or the first regime. Well, regardless of the value of KS plus. So yeah, so we see here this formula, y plus equals to k Reynolds number times y plus blah 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 over the denominator, okay, all right, over this denominator here. This is the same whether we have ks plus equals 2.25 to 90 or ks plus becoming more than 90. The only thing that kind of remains is this big letter g over here. This g here kind of stays, right? This g. Okay, so since this g actually stays around, and g is supposed to be equals to this thing in our equation, then we'll have to take a look at what g is. So let's see the second regime. Let's find out what g is. Okay, because this is important, because from our from comparison, g is supposed to be this much, all right, where kappa equals to 0.41. Okay, so kappa equals to 0.41 is yeah, that's what g is, one of the variables for g. So we'll take a look at what g is over here. So in the second regime, okay, the second regime here, all right, the second regime here is slightly different. Yeah, so no matter what, this g is supposed to be the same as this. Yeah, so in the second regime we see that g is log of t1 times sine t2. So let's just write that down first. From line what? Line 153, g equals to log or ln of t1 times sine of t2, whatever that is, sine t2. So what are t1 and t2? We can take a look here. T1 is equals to C1 Ks plus minus C2. So T1 here, in this case, no, it's not the same as the above. T1 equals to C1 times Ks plus minus C2. Okay. Wow. Looks like a fair bit. And what is T2? T2 is, okay, C3 log Ks plus, okay, minus C4. Okay, C3 ln Ks plus minus C4. So the question now becomes, what is C1, C2, C3, and C4? So let's take a look here. C1 is here. 1 divided by 90 minus 2.25 plus the roughness constant. Okay, what is the roughness constant? Roughness constant. It's over here. Constant is the one that's K roughness, which is 0.5. It's not roughness factor. It is this K. So let's do it. From line where? Line 104. From line 104 onwards, C1 equals to, okay, 1 over 90 minus 2.25 plus K roughness. Okay, that's C1. C2 is 2.25 over 90 minus 2.25. Okay, C2 equals to 2.25 divided by 90 minus 2.25. C3. Whoa, there's an arctangent there. Okay, this gets a little bit more interesting. C3 equals to arctangent, or 2 times arctangent of 1. 2 times arctangent of 1 divided by log 90 over 2.25. Log or ln of 90 over 2.25. Wow. And what is C4? C4 is C3 times log 2.25. C4 equals to C3 times ln 2.25. Okay. And that will just be equal to this 2 times this times ln of 2.25. Alright, wow, that is pretty intense. Okay, so next video we will try and substitute this to find our value of g and see how that actually compares to this expression over here. Of course, in the very rough regime we see a very simple correlation, but over here it's not so simple in the fourth regime. So this actually comes from what is common between both of them, and then we see g is supposed to be equals to this. Okay, this is common among first and second regime, but g is defined differently here. Alright, so let's take a break from this, and then we'll continue in the next video. Thanks for watching. Do leave a like and subscribe if you think it's useful. So all the best, and see you guys next time. Bye bye.